Welcome back. We are now about to begin the sixth lesson in the OpenLI training series. In this chapter, I'm going to introduce you to our virtual OpenLI training lab and show you how to get it up and running on your own machine. Once you've completed this lesson, you'll be ready and able to participate in some hands-on exercises that are going to be coming up in future chapters of this training series. So before I get into the specifics, let's quickly go over the design of this training lab and what you'll be able to use it for. In essence, the lab that we've created is a sandbox environment that you can use to experiment with an OpenLI deployment without having to worry about buying hardware or putting devices into your network. We instead provide Docker containers that run each OpenLI component, as well as a container that will act as a fake law enforcement agency to sync and display your experimental intercepts. The containers are fairly lightweight, and the example intercepts are small and low bandwidth, so you don't need any special dedicated hardware to run this lab. All of the lab containers should be able to run side by side on a single Linux server, laptop, or even a VM. And most importantly, you won't need to tap a network to provide interceptable traffic to the lab. We instead provide PCAP traces that can be replayed into the lab network to emulate real-world traffic that can then be intercepted. Most importantly, the lab will enable you to get some hands-on experience configuring and running the various OpenLI components in a controlled and already tested environment. You'll be able to see the results of your efforts and get used to the techniques that we recommend for validating and debugging OpenLI deployments. You'll also be able to experiment with the REST API for provisioning intercepts and adding LEAs, so you'll be familiar with the API before it comes time for you to integrate it into your own existing management systems. Because the network traffic seen by the lab capture interface is derived from PCAP traces, you will be able to conduct controlled experiments. You can replay specific traffic patterns on demand and confirm that the intercepted records correspond to the packets that you would expect to have been intercepted for that particular traffic flow. You will also be able to upload your own PCAP traces into the training lab and see how OpenLI copes with traffic from your own network. Finally, we've tried to design our hands-on exercises to gradually introduce more complexity over time. So once you learn the basics, then we will show you how to improve an OpenLI deployment to be more robust and secure by adding encryption, authentication, and message brokering capabilities. By the end of our tutorial, you should be well prepared to undertake a deployment of your own on a real network and have proper security and authentication in place. The technology that enables us to create such a training environment for you is called Docker. Hopefully most of you have at least some passing familiarity with Docker and containerization by now, but Docker can be quickly summarized as a system for running applications within their own isolated virtual user space environment, which is called a container, on top of an existing host machine. The containers share the operating system of the underlying host, but otherwise each container will have their own process space, user libraries, and home file system which cannot be accessed by any other container. Compared with traditional virtual machines, containers have low resource requirements and you can easily run multiple containers at the same time on your commodity hardware or even a laptop. Container images can be easily shared and users can easily extend existing images to add additional software components. There's an entire ecosystem dedicated to publishing container images, which is called Docker Hub, and there are base container images available there for just about every Linux distribution that you can imagine. Docker itself is open source and freely available for anyone to use, so it is an excellent fit for our OpenLI training lab. Now the first step in setting up our lab is to install Docker itself. The Docker team have provided excellent documentation that you can easily follow to achieve this. The first link on the slide will give you instructions for installing Docker for your particular Linux distribution. The second link will show you how to configure Docker so that it can be run as a non-root user, which I recommend that you do if possible, and the rest of the instructions on that page can probably be ignored for now. Because Docker relies on the host operating system to run the containers, you will still need a Linux machine to act as a host for your OpenLI Docker containers. This is the trade-off that allows containers to be much more lightweight than a full virtual machine, so you cannot run Linux containers on a Windows Docker install, or vice versa. Once you have Docker installed, Your next step will be to download our lab setup script from the OpenLI Training Lab GitHub repository. You may need to install Git using your preferred package manager first, but otherwise this can be done using a single git clone command, as shown on the slide. Inside the directory that you just downloaded from the git clone command, there will be a shell script called setup.sh. This script will do all of the work of building and starting the training lab containers for you. But as always with scripts that you download from the internet, make sure you take the time to read over the script before running it to make sure that you understand what it is going to do to your system. Once you're satisfied that the script is okay, simply execute the script within the OpenLI Training Lab directory and wait for it to finish. Once that is completed, there will be 4 Docker containers running on your host machine, one for each of the OpenLI components, provisioner, collector, and mediator, as well as a 4th container which is going to be acting as a pretend LEA that will receive and decode your experimental intercepts. Each container will already have the relevant OpenLI packages installed, so you don't need to follow any of the steps from our previous lesson to prepare any of these containers. The setup script has also created virtual networks that link the containers together using the topology that is described here on the slide. Each container is connected to an upstream network which allows them to connect out to the internet. This network can be used for installing software packages or any other situation where you need to download something from an external server. All inbound connections will be firewalled by the Docker host and therefore never be seen by the containers. The 3 OpenLI component containers are also connected to each other via a second network called the OpenLI Lab network. This is the network that will be used by the provisioner to issue instructions to the other components and will be used by the collector to forward intercepted packets to the mediator. Finally, there is a third network called the OpenLI Packet Capture Network. This is the network that is being tapped by the OpenLI collector, and any packets that appear on this network may be subject to interception by our lab system. In terms of interface naming, I've tried to keep things consistent and simple to understand across all of the containers. The ETH0 interfaces provide access to the upstream internet via the Docker host. The ETH1 interfaces on each container are used for OpenLI specific communication between components. The mediator also has an ETH2 interface, which is a direct connection to ETH1 on the LEA container. This link is used by the handovers to pass the output of OpenLI to our fake LEA. The collector also has an ETH2 interface, and this is the interface that will be intercepting traffic from the packet capture network. To access the running containers, you can use the docker exec command to run a bash shell on the desired container. You will need to know the name of the container that you want to run a shell on. Fortunately, we've used a fairly obvious naming scheme for the containers, so it shouldn't be too difficult for you to figure out the names for each container. An example command is given at the bottom of the slide, which will start a shell on the LEA container. Simply swap out OpenLI-agency for another container name to log on to a different container instead. Once you're logged in, you will see a terminal prompt, root at some random set of hexadecimal characters. Don't stress too much about being root on your containers, as Docker will prevent you from modifying anything that is borrowed from the underlying host's operating system. If you do manage to mess up a container, or just want to halt a particular container for some reason, then you can do so using the docker stop command followed by the container name. Do note that any local modifications to the container, including any files that you may have created on the local file system, such as OpenLI config files, will be lost once the container is stopped. So make sure you have backup copies of anything that you might want to reuse before you stop the container. Once the container has been stopped, you can restart it by running the docker run and docker network connect commands for that container that can be found in the latter half of the setup.sh script that you previously ran to initialize the lab environment. If you want to reset all of your containers back to their original state, then simply run the setup.sh script from the OpenLI Training Lab repository again. This will return you to a clean slate for all containers, but once again, any local modifications to any of the containers is going to be lost. So by now you should have a working instance of the OpenLI Training Lab and be able to log into any of the individual containers in that lab environment. Next time we'll take a closer look at the provisioner container and walk you through how to write a suitable config file to get that provisioner up and running. Until next time, thank you for tuning in.